For as long as we can remember, the instinct has been there. On a clear night, step outside and watch the stars. Draw charts, compose diagrams, work out their patterns of motion. Down here on Earth, there was a base randomness to events. Famines, plagues, floods, storms, winters would carry our little lives away as if they didn't count at all. But way up there, in the celestial sphere, things beyond human control and comprehension are surely being decided, and so, thought the astrologers, we might be able to divine the will and intention of the divine, the creatures beyond our understanding, that set the whole grim carousel in motion and kept the horses dancing up and down for their own amusement. And underneath this conviction, this belief that we can stare at the skies for some hint of the plans of the gods, there is another belief. It is better to be governed by some logic, some ironclad rules, some universal temperament, than it is to be thrown around by random fortune and misfortune. We want fate. We can live with fate, but not chance. Yet, of course, as charlatans claim to be able to predict your future from the fact that Mercury was in retrograde towards Uranus, there were cynics then. Cicero, notable ancient Roman silver-tongued windbag, pointed out that twins are born on the same day and yet can have extremely different lives. He noted that, at any rate, since the moon was much closer to the Earth than the fixed stars, the moon would surely have a much greater influence on human affairs if any celestial body did. And he suggested that if everything was solely determined by the positions of the stars and the planets, there seemed little point in developing a theory of medicine to try to treat sick people, or indeed making much conscious effort to do anything at all, since it would all be rendered irrelevant if everything was predetermined anyway. And of course, in a lot of ways, Cicero was right. Astrology can't tell you how to live your life, who you should fall in love with, or when you will die. But in some loose philosophical sense, our ancient instinct was correct. You can tell an awful lot about the ultimate fate of the universe simply by watching the skies. You just need to be a little bit smarter in how you do it, that's all. So this is the story I want to tell, and in classical physical attraction fashion, I've picked a big one. I want to tell you the story of how it is that humanity was able, by watching the skies and by understanding the laws of physics and experiments and theoretical calculations here on Earth, to work out the likely fate of our universe, countless trillions upon trillions of years into the future. And I want to talk about how this same process of inference from this data that pours down from the skies has allowed us to try to understand what the universe looked like a trillionth of a second after it first began. This is the greatest story that we will ever be able to tell, so I'm going to try not to mess it up. In my mind and in my eyes, it is a privilege beyond words that crawling on the planet's face some insects called the human race, lost in time and lost in space, can actually say anything even remotely sensible on this topic at all, let alone map out this grand story, this grand narrative of the cosmos. The question that's plagued me in trying to write about it, though, is when you want to tell the story of the universe, where do you begin? Normal narrative stories begin at the beginning, but in this case, the real beginning is the area that we know the least about, and in some ways has by far the most complicated physics. Even though, in other ways, you can argue that the story of the universe is evolution from a state of extreme simplicity to one of incomprehensible complexity, and gradually back towards one of extreme simplicity again, only this time forever. So perhaps we should start somewhere near the end and try to tell it backwards. But maybe the best way would be to begin as we began, as observers, as a species, as you began, as a person. In media res, that classic narrative trick, where you begin in the middle of a story and then have to flash back or flash forward to learn the rest of it. I don't think there's going to be a correct answer, but I have to start somewhere. So let me begin on the 28th of March 1949 in London. It's 6:30 p.m, and if you turn on your radio, you might just be able to hear what the BBC called the Third Programme. This was basically their more intellectual offering at the time. Sometimes it was criticised for being just a whole bunch of Oxford and Cambridge professors talking to each other. It would be the kind of show where you'd hear the philosopher Bertrand Russell or the playwright Samuel Beckett. That evening, true to form, they had a rising star of physics in Cambridge, Fred Hoyle, outlining to the listeners his own theories about the universe. Part of his lecture went like this. He said, quote, "We now come to the question of applying the observational tests to earlier theories. These theories were based on the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past. It now turns out that in some respect or other all such theories are in conflict with the observational requirements." The reason that this radio broadcast has gone down in history is because this was the first time, to our knowledge, that anyone used the phrase Big Bang. Hoyle coined the phrase to help explain to the listeners that particular theory of the universe's history, but he did not believe in it himself, and in fact he remained one of the most prominent and staunch opponents of the idea of a Big Bang until his death in 2001. The whole lecture was supposed to explain Hoyle's own theory of a steady-state universe, one which didn't essentially start at an individual point of space and time and explode outwards, but instead one that had, in a sense, always been, even if it had always been changing. Some people even argue that the Big Bang was a pejorative, something that was supposed to dismiss and belittle this idea of how the universe originated. While Hoyle insisted that he might not meant to have coined it as an insult, he certainly didn't like the theory. In another interview he stated this. He said, quote, "The reason why scientists like the Big Bang is because they are overshadowed by the book of Genesis. It is deep within the psyche of most scientists to believe in the first page of Genesis." Hoyle made some pretty brilliant advances in understanding the nucleosynthesis of stars, which, appropriately, is where we actually began this podcast back in 2017 with episodes on the life cycles of stars and how they form successively heavier and heavier elements. And he was generally a very well-respected physicist. But he was also a bit of a contrarian, and he liked to hold beliefs that went against the mainstream scientific community, especially in his later years. Indeed, he was one of the people who for a very long time continued to propose the idea that most viruses came from meteor showers or cosmic rays from outer space, and that they were somehow related to sunspots. And you can still find students of his proposing this thoroughly debunked idea in connection to the COVID-19 pandemic today. Yet at the time when Hoyle was confidently presenting his view of the universe as fact, there was still quite a lot of debate about this. But the idea that the universe necessarily had a beginning was not always taken for granted, as it is today. You can see here that we have a scientific question with profound philosophical implications. If the universe has a beginning, it has an age. There was a single point in time when it began. If it began, what triggered the beginning? Why did it begin, and how? What was there before the beginning, if this even makes sense? If the universe hasn't reached a steady state, then this also implies that it can change into something else, that it can, someday, end. Hoyle was being dismissive when he compared the Big Bang Theory to the Book of Genesis. After all, you have to quite loosely interpret any religious text to come up with a theory of cosmology from it. But in one sense, it was an apposite point. These questions about the nature of reality had been in the realm of philosophy and religion for thousands of years. In fact, a theory by Sigurd of Brabant in the 13th century that the universe had always existed was condemned as heretical by the Pope, contradicting biblical teaching. So this had long been one for the philosophers and the theologists. Another example is an ancient collection of Sanskrit hymns in the 12th century BC that posited that the universe had emerged from a golden egg. In ancient Greece, Aristotle and Plato seemed to disagree about whether the universe had existed for infinite time, or only finite in nature. Archimedes attempted to estimate the diameter of the universe, coming up with a figure of around 2 light years, which, as it transpires, is something of an underestimate. Some strands of what you might call Hindu cosmology, theorising about the universe, argue that the universe was in an endless cycle of death and rebirth. But all of this was there for the realm of philosophical inclination and speculation. It was only a few decades before Hoyle's speech that some definitive scientific answers were starting to emerge that had a bearing on these questions. To understand where the evidence for a universe that might not be steady state came from in the 1920s, we need a few extra pieces of physics. First, we need an understanding of cosmological distances. How is it that we can infer how many millions of light years away an object might be? This is one of the first ways that we can extract information from the stars that we look to for answers. Not from the way that they appear to move in the heavens, but from the light itself. We can measure the apparent brightness of distant stars and objects, and if you have good experimental equipment, you can measure this very precisely. We expect, very roughly, but this brightness is going to decrease like an inverse square law as you get further and further away from the source of light. One way to see why this is to imagine a point source of light that's emitting millions of photons, these particles of light, in all different directions. Then you can see that as you move further from the light source, they're spreading out across the surface of a sphere. The sphere's surface area will be proportional to its radius squared, so the same photons are spreading out over a wider and wider area. If you move twice as far away from an object, there'll be 4 times as much surface for the same photons to cover, and therefore you'll receive 4 times fewer photons than you would before, and it will be 4 times less bright. But this is only half the battle, because a priori, without any other information, you have no way of telling the difference between an object that's brighter and further away, and dimmer but closer. You won't be able to tell because they look the same. For example, when you look at the night sky, you can sometimes see Mars or Venus as well as the stars. The planets are obviously much, much dimmer than the stars, but they're also far closer, which means they're both visible to the naked eye a lot of the time. In fact, many of the planets are of course much brighter than the stars. So how can we tell the difference? Well, one way is using something called an astronomical standard candle. You need to find objects where you know exactly what their luminosity is. The luminosity is essentially how much energy the object is producing, so it's related to how bright the object is at any given distance. If you know how bright the object is at its source, and you know how bright it appears to you, then you can work out the distance that it must be away from you. One such set of objects was studied by Henrietta Leavitt, who worked at the Harvard College Observatory for most of her life. She studied a type of stars known as Cepheid variables. Over the course of her career, she discovered hundreds of these stars. Now, they had caused fascination for quite a while because their brightness actually changed over time. You could actually plot the brightness and see that it oscillated over a given period of time with a given amplitude. Naturally, the scientific investigations of these stars were trying to determine why it was that their brightness changed in this way. What Henrietta discovered in 1912 took place when she was examining a set of these stars in the Small Magellanic Cloud, a galaxy close to the Milky Way. What Leavitt noticed was that there was actually, when she examined the brightness of the stars in the period of their oscillation, there was actually a relationship between them. What Leavitt noticed was that there was a relationship between the brightness of these stars and the period of their oscillations. Specifically, the brightness was always proportional to the logarithm of their period. So if you knew how bright the stars were, you could figure out how rapidly they would oscillate in brightness, and vice versa. This meant that all you needed to do was to track the same star over time and see how rapidly it was oscillating in brightness, and then you could work out how bright it was actually going to be. But because all of the stars were in the same galaxy, they were approximately the same distance away. This must have meant, Henrietta realised, that we were actually learning about their luminosity, and not just their apparent brightness. Now we have a simple mechanism for working out distances to various nearby galaxies. We find a star that looks like a Cepheid variable. We measure how long it takes for it to oscillate from bright to dim, and vice versa. Then you can work out what its luminosity is, how much energy it's actually radiating. Then you measure its brightness, how bright it appears to you. Since you know how bright it seems to be, and how bright it actually is, then you can work out the distance to the star. This was one of the first major methods for determining how far away distant celestial objects were. It wasn't perfect. The first estimate was off by a long way, actually. But it was a start that allowed us to work out that the Small Magellanic Cloud was at least 30,000 light-years away. I think this story, like so many stories about observations and experiments in science, is illustrative of the power of pure research. To some people, it might seem pretty irrelevant to the fate of the universe, cataloguing this one particular type of star with its strange, eccentric brightness pattern, painstakingly observing how its brightness changed over time, finding new examples in different galaxies that had the same pattern to it. It might just seem like a form of astronomical stamp collecting, but the insights from this painstaking cataloguing of the details of these stars allowed us to add an immeasurably important tool to our toolbox for understanding the scales, the shapes, and the distances of the universe, and all of the physics that we can then infer from that. So this was one of the first tools that's needed to start the journey to a change in cosmology, and astronomers quickly set about trying to use this to map out the nearby galaxies, determining approximately how far away each of them was from Earth. The knowledge of how the brightness of stars changes over time is enough to tell us this much. Another key tool in this cosmological quest is the shades of starlight. more specifically the frequencies of light that are emitted by certain processes. This is where the assumption that the laws of physics work the same everywhere is so crucial. For example, if we know that the hydrogen atom is the same everywhere, then we know that its structure is the same everywhere. We know from atomic physics that the electron on a hydrogen atom can sit in a certain number of energy levels, jumping between them. We know that atoms can excite when they absorb a photon, with an electron rising into a higher energy level. We also know that the electron can give up that energy and emit a photon to de-excite. Now, when they emit these photons, the energy of the photon is always going to be the exact difference between the energy levels. You can imagine the photons as carrying away the energy that's required to jump between the levels for the electron. And since the energy levels are always the same, the energy of the photon emitted is always the same. Technically, these energy levels can in fact be distorted by various things like magnetic and electric fields, but we're ignoring these complications for now. We know that the energy of light is proportional to its frequency, its colour if you like. Something similar to this happens in a fluorescent tube, like one containing neon gas for example. You pass a current through the tube, the electrons bash into electrons in the atoms of neon, they get excited and then they de-excite over time. As they de-excite, they'll emit photons of that same colour, giving you that monochromatic light that you're familiar with. The universe is full of examples just like this. Clouds of gas that get excited by starlight that shines through them, and then they de-excite, emitting photons of a particular frequency, and hence a particular shade. And this then becomes very important for cosmology and astronomy. If you know the set of bright lines that are emitted by a certain kind of gas when it's heated up, you can figure out the composition of that gas. Or alternatively, if you can see that the light from a star is reaching you but with some bright lines missing from it, you know that something must be absorbing it along the way. This is how we could figure out, for example, what atmospheres of planets circulating stars look like. The history behind these discoveries is also fascinating and worth talking about a little. Joseph von Fraunhofer, Robert Bunsen and Gustav Kirchhoff, who are remembered also for the Fraunhofer diffraction, the Bunsen burner and Kirchhoff's laws of circuitry, were all crucial contributors to the invention of the spectroscope, and the application of this to determining chemical elements. Combining a single slit and a prism, they discovered how to use the prism to split light into its constituent wavelengths. This process, of course, of refraction of light, which depends on different wavelengths, will be familiar to anyone who's used a prism or seen a rainbow in a glass before. Bunsen applied this to chemistry by using the spectrograph to analyse the spectra of light produced by hot gases. He used it to discover new elements in the lab. We now know that he was probing the energy levels of the atoms in these new elements, determining which wavelengths of photon they could release. Kirchhoff and Bunsen used this to observe the sun, which is how it was discovered that the sun was made mostly of hydrogen gas, as the spectrum of hydrogen gas had been observed in the lab already. It was William and Margaret Huggins in the 1860s who combined a powerful telescope with a spectrograph to start to analyse the spectra from faraway stars. By splitting the starlight into its constituent lines, they were able to determine that these far-off stars were composed mostly of hydrogen and helium, just like our sun. And this, in a sense, was the conclusive proof that the stars were not distant pinpricks of light, but additional suns. This was far from the only revelation that can arise from spectrography and analysing the frequencies of light from the cosmos, though. Because, cosmologically speaking, if you know the spectra of the light that you're hoping to find, that you're supposed to find, then you can tell if something has happened to the light on its journey. Vesto Slipher investigated the spiral nebulae, which emit light which can be split into its constituent colours on a spectrum. Lines then appear in this spectrum in particular patterns depending on the elements in the light source. Yet if the light source is moving away from you, the lines are shifted towards the red part of the spectrum. So you might see the same pattern that you expect for an element like, say, iron. You can figure out that pattern from experiments on Earth which determine the energy levels of iron and the frequencies of light that it can emit. But you'd see the whole thing shifted into the red part of the spectrum. This is due to the Doppler effect, familiar for anyone who's ever heard a car approaching and leaving. As something approaches you, the apparent frequency of the sound gets higher. As it recedes from you, the apparent frequency gets lower. Similarly, if an object emitting light is approaching you, its wavelength gets compressed or shorter, and it will appear higher energy, towards the bluer end of the spectrum. If an object emitting light is travelling away from you, its wavelength is dragged out, its frequency is reduced, and it gets shifted to the red. This same Doppler effect isn't noticed by us in day-to-day all that much for light, and the reason is pretty simple. The Doppler effect in waves becomes more important and more noticeable when the source is travelling at speeds that are a significant fraction of the speed of the wave. The speed of sound is about 340 metres per second, so an ambulance travelling at 30 metres per second, or 70 miles an hour, is significant enough to change that pitch in a noticeable way. But the speed of light is 300 million metres per second, so any changes to the frequency of, say, the lights on the sirens will be far too small for us to see, even though of course they do still happen. Analysing the light from these distant nebulae, Slipher found that nearly all of them appeared to be moving away from Earth. Slipher knew that a shift toward red suggested that the body was moving rapidly away from the observer. But he had no way to measure the distances to these reddish bodies. It was only when discoveries like the Cepheid variables were made that astronomers and cosmologists were able to put the two facts together and make a rather incredible inference about the nature of the universe. Every galaxy was in fact rushing away from Earth. Far from being in any kind of permanent steady state, the universe was in motion. In the rest of this series we'll explore what that means. But first we're going to leap back in time and discuss how our knowledge of the universe began. With nothing. Thank you for listening to this episode of Physical Attraction, the first in our Cosmology series. If you have any comments, questions or concerns about the show, anything you'd like to talk to me about, please do get in touch with us and email us via physicspodcast.com on the web. There's the contact form. Any emails I get, I love to try and reply to. If there's anything you'd like to know about cosmology, now would be a good time to tell me. You can contact us in other ways too. You can find us on Twitter at PhysicsPod and on Facebook, Physical Attraction. If you want to help support the show, there's several ways to do that. There are donation buttons on physicspodcast.com. You can subscribe to us on Patreon, where you'll be able to get all of the episodes as soon as they're produced, which can in many cases be many weeks before they are made, and you will get bonus episodes there that no one else has access to. And thank you to those of you who have already supported us that way. Of course, the non-financial way to support us is to leave reviews for the show if you enjoy it on your favourite podcast platform, and of course you can tell other people who might be interested in the show to listen to it, promote it on social media. All of these things really help get the word out, and if you've enjoyed the show, it's a really helpful thing that you can do to help us produce more of it. There are other things for me to plug as well. There is the Facebook page Science Podcasts, where we have a group of many different science podcasters, so if this is only whetting your appetite for science podcasts, you'll find many more there. And there is a subreddit that we have for discussing the episodes. This is reddit.com/r/physicspodcast. So it's the Physics Podcast subreddit for those of you who are on Reddit. No one is there at the moment, but I was reminded that I was supposed to tell people to get involved with this, so please do if that's the sort of thing that interests you and you would like to start the discussion there. Until next time then, please do take care.